Okay, so here is some extra buffer problems, and it says in number 1, which of the following is not a buffer system? So first of all, to be a buffer system, what you need to have is a weak acid or base. It's got to be weak, and then it has to have the conjugate of that acid or base. So if there's a weak acid, it needs to have its conjugate base there. If it's a weak base, it needs to have its conjugate acid there. The conjugates are usually present in the form of a salt, meaning that there's some kind of anion or cation added onto it to make it so it's something that can dissolve and then break into ions. So for example, right here we have fluoride ion, which is F-, and we have hydrofluoric acid. And so this is a weak acid, of course, because it's not hydrohexyl honohexyl H2SO4. And then this is the conjugate base of this weak acid. So this would be a buffer solution. Sometimes you'll see it written as HF, and then there'll be a salt of this. So they'll say there's KF in there. You can ignore the K, of course, because that's in the B of the periodic table, and that's going to do nothing in solution, and that just provides the F-minuses. So A is not the answer. Looking at B, bromide ion, and then hydrobromic acid. So this is an acid, but it is not a weak acid. Remember, hydrohexyl honohexyl H2SO4. And this is the conjugate base of this, but it's not from a weak. This is a strong acid. So this one cannot be a buffer because this is not going to be a very good base at all. It's not going to want to get protons. And so this is the answer to this question. It cannot be a buffer. What about the other ones? Yeah, they can all be buffers. So let's take a look at C just to see why. Phosphate ion is PO4-3, and then the hydrogen phosphate ion, HPO4-2. So you can see that this one would be an acid because it has an H on it that it could donate, and this would be the conjugate base of this acid. And obviously this is a weak acid because you didn't memorize it, just a strong one. Same thing with all these other ones right here. There would be weak acids and their conjugate bases. Okay, and then in number 2, which of the following can be mixed together in water to produce a buffer? So you have to look through here and you have to find one that's weak, and then you have to find one that has its conjugate. So if you look right here in letter B, it's disguised, but here's a weak acid, H3PO4, and then you have to break that up and remember that Na+ is not going to do anything in solution because it's in the B of the periodic table, and remember if it comes from a strong, it's going to be a neutral. And then this is H2PO4-. And so this is our weak acid, and this is the conjugate base. And so B could be a buffer solution. And then in number 3, it's a calculation problem. It says calculate the pH of the solution that's 0.3 molar in ammonia. So there's our weak base right there. And 0.2 in ammonium chloride. So ammonium chloride would be NH4+, and then it'd have some Cl-. Ignore the Cl-, of course, because that comes from a strong, so it's going to be neutral in solution. And now you can see we have a base and its conjugate acid right here. And that's what we need, is the weak base and its conjugate acid. So to find the pH of this, it's easy to use what's called the Henderson-Hasselbalch equation. And remember, that's always on your equation sheet right here. pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. And so if you look at these here, we have our base, ammonia, would go on the top. That's 0.3. And some people say, well, what's the liters that it in? Well, let's just make it up. Let's say it's 1 liter, okay? And the acid is 0.2 molar, or 0.2 concentration per liter right here. If it was in moles, we'd have to divide it by liters. This happened to be in molarity, so I really don't have to do that. But this one right here is in moles, so if I had to convert it to moles, I could just guess on the liters. But notice what happens to them. They drop out. That's why you can just guess on the liters and just put the moles in there. And then you take the log of that, and then you need the pKa, and the pKa is equal to the negative log of the Ka, which they give us as 5.62 times 10 to the negative 10th, and that is 9.25. And so our pH ends up being this plus the log of 0.3 over 0.2. The log of 0.3 over 0.2 is 0.176. We add that to the 9.25, and we end up with a pH of 9.42. There you go. There's some buffer problems to help you out.